Alright, good day guys, how are you all doing? Um, but discussing much more about the linear first order differential equation, and literally it is much more of a particular differential equation that is in the basic of the aspect of a certain first degree of, when I talk about first degree, I don't think anybody should not know that. Are you with me? So it has to be in a certain equation of this form. And we don't literally have much more time of saying you want to start dealing with how do you break it down, how do you get this, how do you get that. We are much more less concerned about that. So the procedure, before we move into the procedure, we literally think of what about if you multiply this particular equation by a constant value, which is, let's say, either b or c. If you multiply everything all through, it will affect all the certain particular equation, right? That's the first thing you need to note. Like I said, we are not moving into breaking it down of, okay, how do this generate in some cases. If you are actually, if you want something like that, you go to some other things that we are going to draw. Now, but this is clear and intuitive. You don't have issues with that. Now, the first thing you have to do is that if the differential equation comes in a form whereby is much more of not something like this, you make sure you break it down to become something like this. How you get what I'm saying? As I said, rearrange the equation to the form above. Now, this and this is the same thing. There's no difference there. This is just q. Q stands for the function of a particular variable, which is x that we are dealing with. Are you get what I'm saying? So the second thing is you now determine the integral of the function of x. That's p standing as a function of x dx. Now, why do we determine the integral of p and not this? Is simply because why we consider by moving our, should I say, our theorem or our proving? Why being considering? We consider that this is what is much more like a factor that could help in order to analyze the differential equation linearly. Now, the third thing is that you now determine the integral factor of the exponential function of integrating the function we have here. Then after that, you substitute it into a certain equation 3. That's whatever you have here as your answer, you substitute it into it. Then the last thing is that then you integrate the right hand side of the equation also to give the differential equation. Then literally, if you are being given boundaries, this is an example. This is not only the boundary that you can be given. Any boundary can be given. Boundary means when you have been setting the value of x being equal to something and the value of y being equal to certain particular value. In that point, that linear equation won't have a constant, and the particular solution to the differential equation can be determined. This is a normal solution to the differential equation. This, when there is boundary, gives the particular solution to the differential equation. Now, what do I want us to just consider here? Now, if we have to consider multiplying all these particular certain equations by a factor, how you get what I'm saying, which is the exponential, which is the they call it the integrating factor. If you multiply all of them through by the integrating factor, you would consider something by saying that you would see why this and this, that's the y dx of multiplying by the integrating factor, multiplying this by the integrating factor, and the integrating factor of this. When you differentiate this function with respect to this, by breaking this down, it gives us this by breaking down. Now at this point, now you have to look at it. You would see that since these two are much more like, what do they call it, a linear term that we can factor. So that's we can put into factor. We can factorize them this way that we can factorize it. E raised for integrating p x ds would be equals to what? The y dx plus what? Y into brackets what? Y then times the function of what? P x. By differentiating this function here, you will see that it will literally bring you back to the certain variable or certain factor of what we have here before. So with that particular possible way, we could understand that this is the integrating factor, and to get the primitive, to put it in the primitive form, that shows that y times the integrating factor will be equals to integrating the function of x times the integrating factor plus the constant c. So this is the primitive, and it is literally whenever you are being given a linear first order differential equation, all you need is the primitive to work out most of the work you are dealing with. How you get what I'm saying? So let's go to some particular example and check out how we can utilize them. Alright, so this is a certain particular first example, and we've gotten a certain equation which is much more of a clear deal. And always our first step is we look for the function of p and the function of q. And we know that the function of p at this point is of 2x. Follow the equation, and the function of q is equals to 4x. IOB. Then also our next step is that we integrate the function of p ds. That's integrating 2x dx. And if you are to integrate 2x dx, at that point, your answer will be giving you 2x squared over what? Over, over 2. Law of integration. And that will be equals to x squared. So what else I want to find is that we literally need to look for something else. And after this, what do? We put it in the integrating factor. Integrating px dx. And that will be equals to e raised to power x squared. Are you me? Then our next step, which is going to be what? Writing down the particular primitive equation. At that point, I think that the primitive term of the equation is ye raised to power integrating px, the x would be also equals to integrating the function of x dx, then multiplied by what? The integrating factor of integrating p x dx. Are you with me? So at this particular point, what do we have to do? We already know that this is going to be y, then e raised to power x squared. The value is substituted into here. This will also be equals to integrating. Our function of qx is going to be equals to 4x. Are you with me? So you have 4x, then e integrated this will give us times e raised to power x squared, then dx. So you have y e raised to power x squared equals to integrating. Since 4 is a constant, it can move out, right? Then you have x e raised to power x squared dx. This is looking like a whereby we can break this down instantly, because at this point, if you have to say u being equals to x squared, we have the u over the x being equals to 2x. Are you with me? And at that particular point, you have the x being equals to the u over 2x. I hope you understand that when you multiply this cross bracket, then you have the x being equals to the u over 2x. 2x. So at this point, you have y e raised to power x squared equals to 4. Integrating x, then times e raised to power u times du over 2x. So at this point, s cancel x, then 2 here. Are you with me? So at this point, you have 2. 4, this will become 1 over 2. So 4 divided by 2, you have 2. So you have y e raised to power x squared, then equals to 2 integrating e raised to power u du. So at that point, if you have to integrate, you know the law of what do you call it, of integration already. You have y e raised to power x squared equals to. So if you have to integrate e raised to power, integrating e raised to power u, you still have e raised to power u then plus c. So you have that will be 2 e raised to power u plus c. So y e raised to power x squared would be equals to 2 e raised to power x squared plus c. So that's the general solution to the certain particular linear differential equation. Now let's check out the second example. Now at this point, you have x dy dx equals to this. Then I told you guys that literally whatever you are doing, you have to consider the point of having the y over dx plus the function of x equals to qx. So it's very, very important. So literally this has actually break it. So you have to put it in the form of something like this. So at this point, if you have to look at it at this point, we can decide to divide all of them by x first, right? But before we do that, let's bring this y to this point back first. So you have x, the y over dx, then minus y equals to s cubed plus 3x squared minus 2x. Then what can we do next after this? Then we can divide all of them by x. So we have the y over dx minus y into bracket. Don't forget to be 1 over x. Multiply everything by 1 over x. This will cancel out. So everything takes over x over x. So this will be equals to s cubed over x plus 3x squared over x minus 2x over x. How are you there? So at this point, you have your dy over dx minus y 1 over x equals to x squared plus 3x minus 2. Are you with me? And then at that point, you know that our function of x, so to maintain the steez level of this y as a positive, we can have this as negative 1 over x. Are you get what I'm saying then? Our qx will be equals to x squared plus 3x minus 2. So what do? We integrate our px, right? And that's integrating, you know the negative will come out now, 1 over x dx. And integrating 1 over x dx will give you negative in x. Are we there? So at this point, our integrating factor px dx, that's e raised to power negative in x. And don't forget from the exponential rule that this is a natural log. This negative, just like you say negative 1, you can reverse it to the top back by saying e raised to power in x raised to power negative 1. Are you ready? Another point, since these two, they are like inverse them, so they can cancel out themselves. E and in cancels out themselves, then you have x raised to power negative 1. This is also 1 over x. Are you get what I'm saying? So at this particular point, we can write the equation back now in the primitive form. So in the primitive form, we are going to be having y. We know y of the integrating factor of the function of the x dx equals to q. So I think that you integrate the function of this also, integrating the function of qx, then times the integrating factor also px dx. Then we can have dx for the equation. So at this point now, our integrating factor is 1 over x here now, right? So that will be y over x equals to, that's y times 1 over x now. So that will be y over x, then that will be equals to integrating our qx is what? X squared plus 3x minus 2, then times 1 over x dx. So if this multiplies everything, we have y over x equals to integrating x squared over x plus 3x over x minus 2 over x. We have dx. So you have y over x being equals to integrating x plus 3 minus 2 into brackets 1 over x dx. So at this point, you know we are going to integrate them one by one. Just integrating x, integrating 3, integrating negative 2, and 1 by. So at this point, you have y over x equals to, you can break them down. You have integrating x dx plus integrating 3 dx minus integrating, you know the constant 2 can come outside, 1 over x dx. So that is it. So at this point, you have y over x equals to, you have x squared over 2 plus 3x minus 2 in x plus c. Integrating 1 over x gives us in x, do not forget that. So at this point, we need the linear term of y. So we can literally, first of all, we have to make sure we clear the term that we have there. Multiplying everything by 2. We want a linear term. So we have y over x. Multiplying it by 2, you have 2y over x equals to x squared plus 6x minus 2 times that, you have 4 in x plus 2c. Are you with me? Then at that point, you know, I told you guys at this point now we can write our constant as c1, so as not to cause any confusion. So at this point you have and you know, don't forget, all this becomes a simple constant. Are you with me? So if you have to multiply everything also by x, you have 2y equals to, that's multiply everything by x throughout, so as to cancel out the x you have here. So you have s cubed plus 6x squared minus 4x in x. Are you with me? Then plus, this becomes a constant c, so that will be plus c times our x. So which means this is actually a normal equation, or should I say general equation for the linear differential um, equation being given.